Okay, back from the coffee break. Yeah, we have image. Before the coffee break, we finalized by presenting the rotation matrix with the axis angle parameters, and I discussed a little bit the problem with axis and angle and different dimension, different physical dimensions. And actually, so let's repeat the equation. Well, I can write it again. So the equation to find this transformation was, of course, we had P prime. Then we had, let's write a plus, 1 minus cosine phi, and then we had this n cross p prime plus the sine phi, and then we had n cross p prime. Now, the parameters we use are these axis angle, but well, Euler was a smart guy, right? So, pretty smart, actually. Far out. So, Euler thought, can I not combine these two? Can I not combine the axis and the angle in some way? And to do that, he first thought, well, I have to use half angles. Now, why you have to use half angles, that's always a sort of a mystery. But it starts like this. Remember that sine 2 alpha is 2 sine alpha cosine alpha. That's one of the things we know. And the other one is the cosine of 2 alpha equals cosine squared alpha minus sine squared alpha. And I'm going to rewrite that by saying that is equal to 1 minus 2 times sine squared alpha. Or, and then I can even rewrite it, I can say, well, from these two, I can think of, because I have a sine phi here and I have a 1 minus cosine phi. And I want to make those products of angles. So, for my sine phi, I'm now going to write 2 times the sine phi over 2 cosine phi over 2, just using this one. And then the other part here, the 1 minus cosine phi, I'm going to get from this expression, right? And that is 2 times, well, you could say sine squared, but on purpose I write sine phi over 2 times sine phi over 2. 2 times sine squared. And then these, I'm going to substitute in these equations. And then you think, well, that's not very thrilling, and nothing much is happening, so I get plus 2, and then sine phi over 2, sine phi over 2, and then we get n cross p prime, plus, and I need a little bit more space, yeah, I can do that here, plus 2 times, then I need this guy, right, sine phi over 2 cosine phi over 2 times n cross p prime. Oh, we put brackets maybe around this. Now comes really the genius of Euler. He looks at this equation and he says, well, I'm going to combine the n with sine phi over 2. Because here I have n and again n, so 2 times the product of n, and I have 2 times the sine phi over 2, and I have here n, and I have 1 sine alpha over 2. So I'm going to define a new set of parameters, and we call those the Euler parameters, and the first set is this, sine phi over 2 times this axis of rotation. So what he does, he multiplies the axis of rotation with sine phi over 2. That's and then, but still we have one more thing which we have to enter, that's the cosine phi over 2. He says, well, I'm going to call that lambda 0. That's my cosine phi over 2. And with this new set of parameters, I now can rewrite this rotation matrix, right? So it's going to be P equals P prime plus, well, the 2 remains, and then, well, for this sign and this cross product, we just can simply write lambda cross p prime, right? Because the lambda already in itself has the sine phi over 2. And then the second part is plus 2 times, and then lambda 0, that's just a scalar, and then we get this lambda vector cross p prime. These guys we call the Euler parameters. And now if we look at the equation and we do the same thing as we did for with putting the tilde matrix for the cross product, we can write again this as I plus 2 times and then lambda tilde matrix plus 2 times lambda 0, just a scalar, times this lambda tilde matrix times p prime. Or in other words, we can write our rotation matrix, again, from the body fixed frame to the inertial frame, expressed in terms of these Euler parameters as I plus 2 lambda tilde plus 2 lambda 0 lambda tilde. Now, a smart student would say, well, so what? I mean, you rewrote one set into a set of another, and not very thrilling. But upon closer inspection, we see that this R is bilinear in these lambdas. So it's a pure quadratic expression into the lambda. So when we're going to differentiate with respect to whatever, we get linear terms. And when we differentiate again, we get constant terms even. Moreover, there are no sines or cosines. We do not have to calculate any sine or cosine term, which seems a bit odd when you talk about angles and rotations. But the thing is, within these Euler parameters. So that is the beauty. Moreover, the parameters are all equal. They all have the same sort of dimension. Well, you could say that's not absolutely true because one is a vector and the other is a scalar. So it's almost right, I could say. So the dimension argument is not so strong. Anyway, we can now put in all these matrices and then find out what does this rotation matrix look like. That's super interesting. Before we do that, there is one constraint, of course. 4 parameters means one constraint. Does anybody know what the constraint is? Looking at these parameters. Yeah, exactly. So if you add all the squared of all these guys, then in the end you get sine squared plus cosine squared, and that should be 1. So they should be 1. So the norm of the thing should be 1, which is pretty easy to drag along. So saying lambda 0 squared plus lambda dot lambda should be 1. That is the constraint we have to drag along. That's not so difficult. Then we can put in this this cross product and the double cross product of this one, which is actually sort of fun to do. So the cross product was this one, lambda 1, lambda 2, lambda 3, and then minus lambda 1, minus lambda 3, minus lambda 2. So that is that guy. And if I remember well, if we do this double thing, we got this strange matrix with which looked a lot like this inertia matrix. But then minus lambda 2 squared, minus lambda 3 squared, minus lambda 3 squared, minus lambda 1 squared, minus lambda 1 squared, minus lambda 2 squared. That was on the diagonal. And then the off-diagonal terms were lambda 1, lambda 2, lambda 1, lambda 3. And of course it's symmetric, lambda 2, lambda 1, lambda 3, lambda 1, lambda 3, lambda 2, and this should be lambda 2, lambda 3. This had a lot of resemblance with the inertia tensor. the integral of these two products. Anyway, taking these two, substituting that, and using the identity, using 1 equals lambda 0 squared plus lambda 1 squared plus lambda 2 squared plus lambda 3 squared, you finally get a nice expression for your rotation matrix, which looks like this. Lambda 0 squared, and then plus lambda 1 squared minus lambda 2 squared minus lambda 3 squared. Then the second diagonal term is lambda 0 squared plus, no, that's not a plus, that's a minus. Minus lambda 1 squared plus lambda 2 squared minus lambda 3 squared. And the third is lambda 0 squared, a little bit more space, minus lambda 1 squared minus lambda 2 squared plus lambda 3 squared. So it's highly systematic. Then the off-diagonal terms, well, the off-diagonal terms, looking at the original expression, you can easily cook them up, because one part has to do with 2 times lambda 0 and the cross product. So in the off-diagonal terms, we need this lambda 0 times 2 times all these entries. They come here. But not only that, we also have to take these terms times 2. So just add these plus lambda 0 times this, and then put a 2 in front of them, and we're there. So let's take this one 2 times. So first we take this term, so we have lambda 1, lambda 2, and then we take this guy, we get minus lambda 1, lambda 3. Let's take this entry, so we get 2 times, well, we first take this guy, so that's lambda 1, lambda 3, and then we take lambda 0 times this guy, plus lambda 0, lambda 2. Then we go to the next row. Well, the fun is that the next row, we have this identical thing here. So again, we have lambda 1, lambda 2. But since the cross product now has a plus, we get plus lambda 0, lambda 3. And here likewise, we need this entry, lambda 2, lambda 3, and then the minus lambda 0, lambda 1. And we finalize by saying the 2. We start here, lambda 1, lambda 3. Then the cross product minus lambda 0, lambda 2. And this guy, lambda 3, lambda 2 plus lambda 0, lambda 1. Now, why do I take the effort to write it out? To show you that that's highly systematic how this matrix is formed. So, and we see also that, of course, it's not asymmetric, because there's a symmetric part in it and an asymmetric part in it. It's bilinear, clearly bilinear in the Euler parameters. And actually, if you go deeper into this, you come to the conclusion that you can really form this matrix as the multiplication of 2 matrices which are just linear in the Euler parameters. So there exist 2 matrices, linear in the lambdas, and if you take one times the transpose of the other, you get your rotation matrix. And to find out how that works, you need a little bit higher algebra than we know now. You need Quaternion algebra, because Euler parameters are a special case of quaternions. They are unit quaternions. And so a quaternion is something with a scalar, Q0, and something with a vector part. And quaternion calculus is how do you multiply these, how do you add them, and actually with these quaternions you can easily build matrices by which you can make rotation matrices. And you can use these quaternions also to make composite rotations. By doing quaternion multiplication and addition, you can get the resulting rotation. It's in the book. I'm not going to discuss it in the lecture. For now, let's look at nice quantities like we have the rotation matrix. Let's go back to my formulation. So I plus 2 times lambda tilde plus 2 times lambda 0 lambda tilde. And remember, lambda 0 was this cosine phi over 2, and the lambda was this sine phi over 2 times the axis. Now what if you want to find r minus 1? How do you do that? Why? No, you say it's a transpose, and somewhere in the theory you can read, yeah, the inverse is the transpose. I have no clue how that works, but they say so, right? Because it's an orthogonal matrix, and then a lot of theory, you have to crank out a lot of theory to show that. But why not just use your common sense? We have an axis, we have an angle. So if you want to rotate backwards, which is r minus 1, then that is saying, well, the angle becomes minus the angle, right? Why not? And that means for the Euler parameters that the lambda 0 remains the lambda 0, and this lambda vector becomes minus the lambda vector. Correct? So that's rotating backwards. You could also say, no, we don't do that. We take the same angle, but we flip the axis. So instead of this axis, I take this axis. That's also rotating backwards. Well, you can do that. If you do n goes to minus n, you will see finally you will get the same result, of course. Right? So rotating backwards, meaning in Euler parameters, just negate the vectorial part. And if we negate the vectorial part, what do we get? So apparently rotation minus 1 is, well, this remains the same. If we negate this once and we negate it twice, well, as you can see, minus lambda tilde times minus lambda tilde. Nothing much happens, eh? And then here we negate this once. Then apparently the result is I plus 2 times, here we have the same, lambda tilde. Those two minuses, they go away. And then minus 2 lambda 0. And then that's exactly, of course, rotating backwards. Or in other words, that's if we take the transpose of the matrix, well, I transpose is I. If we do the transpose of this one, we get minus the one, and again minus, so we get the same. That doesn't change. And if we do the transpose of this guy, we have to put a minus sign for that one. And we see we get the identical result. So this again shows you that the whole concept of axis angle is far more intuitive than Euler angles. So my guess is that Euler started with Euler angles and then later on developed the whole concept of Euler parameters, but I'm not sure if that's true. So the last part, which we still have to resolve, is the problem we had. Because why are we doing this? Not because we like to sit together here and talk a lot of mathematics and so on, but we had a problem. Our problem was gimbal lock. Or, and the big question is, do we have that same problem here? Or in other words, can we form a relation between the angular speeds and the Euler parameters themselves and the time derivatives? What is the relation between those two? And can we flip from one set to the other easily without any singularities? If we can, then the whole gimbal lock problem is solved. Now we have the definition, of course. R dot R transpose is this omega tilde, right? And from that one, you can, of course, develop what are these expressions, because you can take the partial derivatives here, dr d lambda 0 lambda dot plus dr d lambda 1 lambda dot 1 plus dr d lambda 2 plus dr d lambda 3. And then everything times R transpose, and that should be then this Q-symmetric matrix. That is a way to go. It's lengthy and error-prone again. And there is actually a shortcut, and the shortcut, in this case, unfortunately, goes by Quaternion algebra. So if you want to know how the shortcut is, then you have to look into the next chapter in the book after this. I'm not going to talk about it now. But that demonstrates how Quaternion algebra works, and then pretty simple and clear you will find these expressions. But you can also go this route. And of course, plus you always have to use this identity, right? So lambda I is 1, or in other words, lambda I is 0. Or in other words, the change in the Euler parameters is always tangent to the Euler parameters themselves. Okay, if we do that, then we get the following set of expressions, and I'm just going to present the result here because it's undoable. So we have lambda dot 0, lambda dot 1, lambda dot 2, lambda dot 3, and we get here on the right hand side omega x, omega y, omega z. That I extract from this, and the expressions look like this: minus lambda 1, minus lambda 2, minus lambda 3. Then on the diagonal we have lambda zeros, and on the off diagonal term, yeah, it's almost unbelievable, you have this skew symmetric part. So that is if we apply this, finally we get this result. So we get a nice expression of omega, and in this case it's the inertial fixed angular speed, in terms of the Euler parameters and the time derivatives. But of course we want to know it the other way around. You always, what you have is not what you want, you always want something else. So what we want is this. Lambda dot 2, lambda dot 3 equals something times these omegas. And the big thing is, what is this matrix? Now then we have to invert this one. And can somebody do that? Not really, eh? But remember, we have a constraint, right? Yeah. So although you think you have 3 equations, we have 4 equations. So let's add the 4th equation. And I'm going to add it on top of here. So that means lambda 0, lambda 1, lambda 2, lambda 3 times this guy is 0. Right? Now we have this nice matrix, and now we can do the inverse. I forgot there's a 2 in front of it. Remember, there's always a 2. Yeah, what does the inverse look like? Well, there's 1 over 2 here. And then lambda 0 minus lambda 1 minus lambda 2 minus lambda 3. Lambda 1, lambda 2, lambda 3. Lambda 0, lambda 0, lambda 0. And the entries we have here: minus lambda 1, minus lambda 2, minus lambda 3. And lo and behold, if we call this matrix like this guy, capital lambda, then apparently this is capital lambda transpose. So they're sort of an orthogonal matrix in 4D or something like that. But the main thing is this: without singularities. And that is a very important thing. So now when we do our calculation, everything is nice and smooth, and we do not have to reformulate our rotational parameters. Of course, in our whole calculus, we have to drag along your constraint. And you can set up the constraint equation of motion in that sense. So, and how do you do that? Well, you have to do numerical integration, and then you have to do a coordinate projection. But in this case, the coordinate projection is pretty simple, because it's locally on the 4 Euler parameters. So your coordinate projection breaks down to the following thing, that you say I have an estimate. So this is an estimate on my Euler parameters. And that's n+1, the estimate. And if you determine the norm of these guys, then probably they're not equal to 1, so they're a little bit off. But you just renormalize the whole stuff. So what you do is, you say, well, lambda 0, lambda vector is becoming, and then you just take the old ones, lambda 0, lambda vector, and you just divide them by the norm of these guys. And that's it. That's your whole coordinate projection method. That's the shortest route to get back. So just renormalizing. And that works, of course, because you only have one constraint. So that's a pretty simple way of keeping your coordinates on the constraint surface. Now, with that ingredient, you are now able to do homework assignment 10. And I'm going to talk a little bit about homework assignment 10. Yeah, that's this one. So what is homework assignment 10? Well, it's a lot of text, but let's do this. So this is an attraction at the fair, or fair attraction. You have to pay money to experience this. You are in a cage, and there are 2 bungee cords left and right, and a magnet is holding you down, but then the magnet releases you, and this is what is happening. Some people like it, and as you can see, the thing, well, of course you get accelerated pretty quickly, so your accelerations are high, but you're also tumbling, and apparently that's nice. I don't know, people pay money for this. Now when you are a designer, you are stuck with a problem that, and then we go to the assignment again, yeah. So when you're a designer, you have to design this machine. Meaning you have to know what the height of the towers is. You want to know how high are we going to propel the people. Meaning you have to know what type of bungee cords shall we use. It's not that you go to the store and say, well, no, that looks about right, let's do it. You're an engineer, so you're going to calculate. So there are boundary conditions, and one of the boundary conditions is the maximum acceleration you can put people into. The other boundary condition is, if the thing doesn't tumble and rotate, then it's not fun. So make sure that it tumbles, please. So as an engineer, you have a number of problems, and that's what this assignment is about. With all the knowledge you have now, you can make a multibody dynamic model of this with the springs and the body. It's actually pretty simple. And then you can have a state vector, you can integrate the motion, you can see what is going on by just simulating, because it's highly nonlinear. And before you do that, of course, you have to make some estimations here about the chord, etc. Then you do the simulation and you check your estimations. Then you do some checks on, is my calculation correct? Otherwise I'm going to build a thing and people get propelled with 20 G and I have a lawsuit. So that is the assignment. Pretty okay, I guess. That's for next week. Homework assignment. Yeah, let me see my schedule, because I had a whole roadmap for today. Yeah, that is the problem. And then we have the exam. So now I want to go to the exam. And how do we do that? We go to Brightspace. And then we go to our course. And then in the course I say something about the digital exam, that I have here the exam. Yeah. Now I think it's good to talk a little bit about the text here. So what does it mean in words, in short? It means there is a digital exam and you have 3 hours and you get 3 problems. 3 problems. And the problems look a lot like your homework problems. And then it's in MapleTA, you have to give a numeric answer. And you can use all your homework stuff on your USB stick. You can take all the books you want with you. It's individual, you cannot communicate with each other, but you can take all the stuff you want. MATLAB files, Python files, I'll make sure Python runs. And then, well, if you have done the homework and you understood what you have been doing, either by copying things and understanding or by doing it yourself, you should be able to do those 3 homework assignments. Those 3 exam assignments. And we will look into detail to an example of how does it look like. But for now, how do you get your grade? That's the most important part. How do I get my final grade? Now, if your digital exam result is higher than everything else, that's your result. So if you score a 10 out of 10 on all 3, you get a 10 out of 10. Or 8 out of 10 in your homework is less. Now, if your digital exam result is lower, then we have the rule that the 70-30%. So 70% on your weekly work and 30% on your digital exam. So your weekly work helps raise your grade from the digital exam into a final grade, which is maybe a pass. And what is the weekly work? Well, that's for 90% your homework and for 10% the in-class quiz. And what is the homework? Well, the homework is the average of the 9 out of 10 best. So the 9 best of your homework. So the lowest just drops out. Sometimes the cat died or you were ill or whatever. And the same with the in-class quiz. Just 1 drops out. Okay, so that is how we calculate the grading. And my experiences from last year, there were a number of people who really had a higher grade on the digital exam than all the averages on the homework. So that was good. So what does the digital exam question looks like? Well, I finally got it working MapleTA in Brightspace, and it looks like this. Blah blah blah, how many attempts, and not interesting. Well, you should read, of course. Okay, it looks like this. So what do we see? We see it looks a lot like homework assignment 1. It's a double pendulum and then a lot of text. So 2 bars and then some mass moment of inertias are given, and then apparently some length and masses and anyway. And what do I have to do? Question: determine the angular acceleration of the first bar just after the system is released. Oh yeah. So this is the state of rest. Now gravity. I have a bang. Gravity is on. And then the thing starts falling down. Yeah? Down, Down is now apparently in this area, not there. Down is not there. Down is apparently now here. And then the question is, how I ask an acceleration. Now, a lot of people will think, yeah, but if you make a small error in your calculation, my God, then you did all this work. I knew all the formulas. The model was completely correct. But I had one small sign change, and then I got no points. Well, that's not true. If you give the wrong answer here, then it says to you verify. Then it tells you, well, the answer is wrong. Check your calculation. And as you can see, you still have 9 points out of 10. So you only get punished for 1 point. Then, well, you redo your whole calculation, and yeah, now I know. Of course, it was -10. Stupid me, everything is falling down. Verify. Bugger all. Wrong answer. Hints. I get a hint. Remember that gravity is pointing down. In this configuration and loading case, you expect no angular acceleration of bar 2. I had an angular acceleration in bar 2, so I made an error somewhere. Moreover, the vertical acceleration of bar 2 should be twice that of bar 1. I didn't have that either. So let's redo the calculation. You redo the calculation. As you can see, you have still 6 out of 10. Pretty good with the help. So now if you put in the number, you say, yeah, it was 12. Minus 12. I really made a mistake. Verify. Wrong answer still. And then check your calculation, like, oh, with the help, you probably still made some small arithmetic error. Or so this is your last chance, 5 out of 10, right? So now you have to give the correct answer. And I think I had the correct answer somewhere. I don't know if it's correct. Who knows? Minus 14.7. Yeah, was correct. 5 out of 10. So I show you this so you know, yes, I ask a numeric answer, and no, it's not about how good are you in calculating stuff only. I sort of help you if you have content problems. And so I think it should be all doable, the exam. Any questions here now in the room? Because this is the last thing I'm discussing now. Yeah. Yeah, in the back.
We will have calculators along with us or not?
The question is if we have calculators with us. Well, you have a whole computer, and on the computer you have MATLAB. And MATLAB is sort of a fancy calculator. So you have everything. Or if you are a Python guy, you have Python.
Will you specify how many digits?
Yeah, question is, will I specify how many digits? In the beginning, there's a preamble for the test, and it tells you how accurate you have to give your answer. I don't know by head what it was, so, but I think 3 digits or something. It comes down to 3 significant digits, something like that. Other question, yeah?
Yeah, but it's not about the test. When you have defined in the previous case lambda, why only with respect to an angle? You don't have 3 angles. How you choose the angle?
Yeah, okay. So this is about the Euler parameters. I will do it in a personal communication because it sort of breaks my whole thing here. Questions on the exam?
So if you have to put in 3 digits and you enter 4, is then automatically wrong?
No. No. The more digits, the better. No, that's not true, of course, but it's within this. So what it checks, it has the correct answer, and it is within limits of plus or minus. I don't dare to say 5% is not correct. Some percentage, but it's mentioned in the beginning. Yeah.
We are allowed to run our MATLAB scripts in this MapleT, but if for some reason I miss out on some subroutine that I had coded earlier, would we have the flexibility to code it on the spot?
You can do anything. So the question is, if I have my MATLAB scripts and I'm doing the test, can I then code anything? Yes, you can. You have just a computer which has a PDF reader, a Word reader, MATLAB, Python, I think even a calculator, but you don't need that then. But no internet connection, of course, because we don't want you to communicate. And it can read your USB stick. Now, my experience from last year is it is smart to have an alternative media with you, because sometimes the USB stick is not read well by the computer, and then you get like, oh, wow, what do I do, and panic and so on. So it is sort of handy to have a second USB stick for who knows. Yes, question.
Do you need to have a 5 for the exam to pass the course?
The question is, do you need a minimal grade for the digital exam? No. No. You don't.
You have enough grading at the homework?
If you have a very low grade on the digital exam and a high grade on the homework, then you can have a pass. But you have to come to the digital exam to get a final grade. It's the exam. But you can come and put in zeros everywhere. That's okay. Not smart. No. Any other questions? Okay, then we finish the lecture series and see you all at the exam.